Hello, everybody. Welcome to Group 5 Critical Design Review, sponsored by Ocean Insight. Our senior design project for this summer is Water Contaminant Analysis Raman Spectrometer, aka WARS. Our team working on this senior design project from left to right is George McDonald, Photonic Science and Engineering, Julia Smith Blanchard, Photonic Science and Engineering, Sebastian Johad, Computer Engineering, Gibran Khalil, Electrical Engineering, and Juan Vespro Diaz, Electrical Engineering. Like I said before, this is our project, a water analysis spectrometer. An overview of this is to make a device that will be able to recognize and detect contaminants in water. By analyzing the amount of light through the samples, this can be detected.
Ocean Optics has provided our team funding, as well as accessibility with experts in science and engineering to assist us with our project. Our team would like to take a moment to thank them for their guidance and willingness to work with us to make our system a reality. Ocean Optics, thank you.
The motivations that we have for creating this project is have a way to detect contaminated water in numerous places. Due to water being an essential resource on Earth, knowing which ones to drink is essential for not getting an illness. This is why we decided to create a water quality analyzer. Our project goals is to build a portable, cost-effective spectrometer that will focus on measuring different contaminants. With some of our constraints and sponsor needs, the device will be less expensive than models currently in the market. The size of the spectrometer will be portable but not too bulky. Also, the device will be simple and not overly designed. These goals will ensure that we are able to identify the presence of contaminants and be able to have a working product.
The core objective of this project is to produce a system that is capable of performing Raman spectroscopy. We will do this by developing a compact spectrometer as well as designing an illumination system. The advanced objective is to use a combination of a well plate reader as well as with a detachable spectrometer to achieve a modular setup. By using a 785 nanometer wavelength laser, we can reduce fluorescence and better observe the spectrum of our sample.
Our project has many engineering specifications, but these are what we consider to be the most important ones. As you can see, there are three highlighted rows. These specifications will be presented in our demo later on. These specs are being able to detect the presence of three different contaminants in the water sample, our laser having a wavelength of 785 nanometers, and the dimensions of our spectrometer being approximately 3.5 inches by 2.5 inches by 1.2 inches.
Our project features include a computer application so that basically anybody can use it, and it should be very self-explanatory. Contamination detection is also a very important feature for us since we do want to see if the water that we are conducting Raman spectroscopy on is very clean and not contaminated. Moderate speed, we want to be able to scan water samples fairly quickly without a lot of delays. So get a quick answer, is this water good or not? The X and Y table, which allows us to do multiple samples repeatedly and also save the data according to each sample, since the XY table allows us to control fine granularity for the sample's movement and also allows us to measure more than 5 samples instantly without having to switch things out. So our workload was split upon all of our members equally according to their majors and also their strengths. For example, we only have one computer engineer, Sebastian, and he was the one that did all the computer design, programming stuff, just make sure all the software works. Me and Juan are electrical engineering students, so we did all the electrical stuff like the physical safety systems and how they're powered, the precision motor, how to integrate it into the system, and also power supplies and thermal sensors and humidity sensors that we did. Our optical engineers were put on duty for all the optical design components, so things like laser lenses, gratings, and the heterodyne spectrometer, spatial heterodyne spectrometer, the modeling thereof, searching for their components, since that is their area of expertise. So we just split it off into the most, how do you say, appropriate roles.
Hi everyone, this is Juan Restrepo. In this slide, we see the block diagram of the overall system. We can see the many subsystems that we have, such as the power control, illumination system, spectrometer, and the data processing. Now in the bottom, we can see the work distribution for each of these. Of course, we also work together for a lot of them, and yeah.
This is a very brief introduction to Raman spectroscopy. It is important to understand that Raman is a very weak signal that is scattered when light causes molecules to vibrate. Some light remains at the same wavelength, and a tiny fraction shifts in wavelength. This is the Raman signal. Our spectrometer has very high throughput, making it attractive for Raman. When analyzing the intensity and wavelength of the material, one can uniquely identify that material.
Spatial heterodyne spectrometer, or SHS, is the design we are using for our project. This will be used with Raman. Even though Raman has a very weak signal, it can uniquely identify materials, which is a pro for what we are trying to accomplish with identifying contaminants. SHS has a very large throughput, and this is why it is attractive for Raman. The SHS collects light through two diffraction gratings, and when the image is formed, it makes fringes which can be measured.
The SHS accepts input light, which reaches two separate gratings. Each grating diffracts the source light. Wave numbers or frequencies or colors are dispersed. The way light diffracts is described by the grating equation at the top. The Littrow wavelength is the wavelength that produces a parallel wavefront, or in other words, where the first diffracted order is redirected back along the path of incidence. The grating must be tilted at the Littrow angle to accomplish this. Resolving power dictates resolution, and spectral range describes the wavelengths that can be imaged upon the detector. Note that our spectrometer does not produce a conventional spectrum, rather it is encoded within Fizeau fringes that can be described by the fringe equation. One of the design challenges was to keep our SHS compact in size. Ultimately, there was a trade-off between resolving power and spectral range, which are inversely proportional to one another. Our proposed solution was to use a longer laser wavelength in keeping our grating size small, as well as increasing the groove density of that grating. By selecting the grating, detector, and laser, a variety of factors can be determined. Our gratings are to be ½ inch in size. They will be mounted upon a 16mm cage system. This cage system is used for easy alignment and positioning of all of our optics. By modeling the SHS in Zemax, we determined our grating angle to be 6.76 degrees, an achieved resolution of 0.1 nanometers, and a spectral range of up to 885 nanometers.
This slide shows the comparisons of the diffraction grating selections. Ultimately, we went with the first option because it has a blaze wavelength of 760 nanometers, which would work for our laser, which is in the near-infrared spectrum. Also, the peak efficiency is great, and with the group density being higher, it will also give us more information about the fringers. Talking about diffraction gratings, this is a graph that shows the peak efficiency based on the wavelength. This shows that the grating that we have chosen would have an efficiency around 785 nanometers, which would be around the 70 to 75% range. The grating that we have chosen is 300 lines per millimeter. It's not specifically designed for NIR, but with this groove density, it was within our budget and has a great range of what we are looking for. This slide shows the comparisons of the beam splitter selections. The beam splitter that we have chosen for this project is the CCM5 BS017, non-polarizing. The reason that we have chosen this is because we want all the information coming from the diffraction gratings. Every wavefront is to combine and interfere, and this will make an interference pattern when it is on the detector. The wavelength range is 700 to 1100, which is great for our project. This shows the data of the beam splitter that we have chosen. On the graph, it shows the transmission based on wavelength. Since our laser is 785 nanometers, the beam splitter would be good to have since it is and has a peak around the wavelength of our laser. This would be good for getting results and measuring the analysis of the contamination. This is the laser selection. Even though the laser was given to us, we still wanted to compare it to other lasers. So the laser that was given to us was the L1C 785 Oxyus. This laser communicates with PC through serial commands, toggle emission, shutter, and intensity remotely, and the user may control the laser through a GUI. The collimator lens is important to our design because it changes the divergent point source to a parallel beam. The reason we want this is to be able to capture all of the light and be ongoing into the beam splitter. I found a collimator package instead of designing one which would work for the limits of our spectrometer and has a tunable focal length.
This is the lens design that will capture the fringes. It will image the grating directly across the detector. There are two achromatic doublets to improve spherical aberration, as well as an aspherical singlet. All glasses are off the shelf, 1 inch in size, and selected to operate within the near infrared. The distance between the lenses are varied, and provides the degree of freedom necessary to optimize the image quality. Our lens design has an overall magnification of 1/4. The gratings are about 12 millimeters, and the vertical dimension of the detector is about 3 millimeters. The grating is about 75 millimeters from the first surface of this lens, while the image forms about 3.4 millimeters from the last surface. The total optical track length is about 99.6 millimeters. All three lenses will be housed within a lens tube barrel, along with an iris placed between lenses 2 and 3. This iris is the limiting stop of the system and will help improve the image quality. The illumination system is composed of a laser, notch filter, a dichroic mirror, a focusing lens, as well as the illuminated sample. The block diagram is basically an exploded view of the Raman probe seen below. The dichroic mirror reflects some of the light, which is then focused upon a sample. This light is then collected and passed through the dichroic mirror, where a notch filter rejects the 785 nanometer wavelength, where then it is carried by a collection fiber into our spectrometer to be processed. These are the key components of the illumination system. These components span across a few of the compartments of the overall device. The notch filter is actually housed within the spectrometer and mounted upon the 16mm cage system. The laser sits inside of this drawer with a variety of other components. The well plate sits upon a reservoir at the top of the device. There are round cuvettes within the well plate with flat strike surfaces on the bottom. It's important for the surfaces on the bottom of the cuvette to be flat because the Raman probe has laser light that emits beneath the well plate.
On the left shows the layout of the optical components, which includes the illumination system and the SHS. The illumination system includes the laser and the samples, and the SHS, which is the spectrometer, is the input of light and the detection of fringes on the CCD camera. This is an optical simulation and inverse transform result done in Zmax. When the fringes are imaged upon the detector, it will look like interference patterns. The image processing will be done in MATLAB. When this is done, the final result will show a spectrum and can be identified which contaminant was just analyzed.
This is our hardware block diagram. It starts with the power supplies, one of them going into the microcontroller, which has temperature and humidity sensors attached to it. In addition to that, we have a cooling fan and safety interlock attached to it as well. The safety interlock for locking the system when in operation using the information coming from the computer, which is the brain of all of it. The cooling fan just keeps everything cool as needed. The computer controls the XY table controller, which controls the XY table to move the samples as needed as it's scanning, and uses the laser to actually conduct the spectrometer function of our project. Um, that laser goes into the detector, which then feeds back again into the computer so we can display all the data for whoever's using the system. And last but not least, there's also a laser power supply that came separately with it, so we added that as well.
In this slide, we talk about the humidity and temperature factor, which we believe are key concepts in the performance and accuracy of our spectrometer and system as a whole. A reason for this is that we will be dealing with water samples, and which can provide moisture to our system, which would require ventilation. So the way that we are dealing with this is by adding a temperature and humidity sensor that will be connected through the microcontroller by communication I2C, as we see the I2C protocol, to the fan to control it. A requirement for the fan was for it to draw less than 500 milliamps for it to be properly switched on and off. We also see the comparisons of the many different sensors that we had in mind. We ended up going with the one we did, which is the HIH 6030. The main reason for this was because of his package size, which was the SOIC 8, and the reason for this was because he has external pads, which makes it better for troubleshooting and testing. In this image slide, I'm showing the whole PCB layout for the whole circuit board, and we can see on this top side we have the PSU connector, we have the rails for the 3.3, the 12 volts that are powering the different peripherals that require them. We have 24 volts down here as well for the latch connector and the USB layout. And we'll be going more in depth on each of these in the following slides. So these PCB layouts and schematics were done using Altium Designer, and most of the designs for the many peripherals, the logic of it was made through manufacturer recommendations, based on the many components that we have and what should be supporting them. Um, the main reason that we're using Altium Designer was because we thought it was a challenge to learn, since it's not something that we saw in school, and because it is an industry standard to use Altium Designer for PCB designing and building. So yeah. So a quick overview of the power distribution. As previously said, we are running off of 24 volts from our main power supply. It actually runs on 3 amps, as we see on the comparison table on the right side right here. We are using two buck converters. They are the same manufacturer part, but we have two of them for the two different rails. So we're using the 12 volts and the 3.3 volt rail. So the layout for this component was done using the manufacturer recommendation, which is to keep the current loop as tight as possible, as we see here, for dealing with the frequency and the whole reliability of the rail not being affected. And the reason that we went with this one instead of the other ones was for the simplicity of the Webench outputting the this design for us. Now, as for the microcontroller programming, we'll be using the MSP430FR6989, which is one that we are familiar with, as this is the one that we previously worked with in our embedded systems class. And it is the main reason that it was chosen over the STM32, since it is something that we are familiar with and it had an easier way of being programmed within the circuit board. And this is by the use of SPI-by-wire technology, which only requires us to use the SBW-TCK and the SBW-TDIO pins coming from the microcontroller that are to be connected into a development board that one of our teammates owns, so we already have that programming capability in our hands, and that is the reason that it was chosen. Logic gates are used for the signal reinforcing going out to the many peripherals that we need, such as the signal fan and the latching connector. At last, for the main peripherals in our circuit board, we have the USB layout. Now, the USB layout may sound the simplest one, but it's one of the most complex ones based on design, since we have to use differential pairs that require trace specifications, such as them being symmetrical, connecting the data outputs coming from the USB and going to the PC. We are using this peripheral to connect the microcontroller to the PC for data transfer, so we can manipulate data that we get from the many other peripherals, such as the humidity and temperature sensor, to be sent over to the PC for our own purpose. Um, this uses UART to USB connection, which is done here. The translation is done here. It uses isolation as well, since we have a digital ground as the layer here, and the actual main ground for the circuit board on this other side. And this is done by the SI8622 component that is its purpose is to isolate. We see the differential pair here in the schematic, and this is the translation device for the data. We also use LEDs to make sure that the translation is happening um, as we want it to.
The safety interlocks that we have is two of them specifically. We have one of them on the laser, and we also have another one that physically locks the enclosure while the laser is in operation. The one that cuts off the laser is that if anybody accidentally opens our enclosure, it makes sure that the laser stops working. But that also cancels out whatever you're analyzing at the moment. So we added the physical lock partially as a double safety feature, since having only one safety interlock causes a single point of failure, which is very undesirable in safety specific applications, especially when we're working with laser that can blind you within a few seconds. So the physical one stops people from opening and doubles up as safety as well. And also, so the analysis itself of when the lasers are firing can be interrupted, so you don't lose that as well. We had many options for safety interlocks. If you go on Mauser.com and look for them, you get thousands of results. I narrowed it down to these three mostly because of price concerns, and also I wanted one thing that worked with the 24-volt power supply that we have already. So what ended up happening is the main specification I chose it from ended up being the clamping force, just because I want to be able to hold the enclosure closed as much as possible. And if you really put your weight into it, you might be able to cross the 1200 and 1500 Newton forces, but I don't think 3000 is that possible for people. It also happened to be the cheapest, so it was the clear-cut choice by the end of it. Our XY table allows us to move the samples around and have multiple samples instead of having to have one sample water that you have to constantly swap out every minute, which adds into not only the tediousness of scanning multiple things, but also the safety aspect since you're constantly opening and closing it. And what it does is allow us to move the samples with micrometer precision, and that's very necessary, especially due to the fact that the well plates themselves and the wells are about 3 millimeters in diameter, so which is why it's necessary. So these were the options for XY tables that we were looking at originally. One thing that really was very obvious was that they happen to be very expensive. So price was not really a consideration, given that they were all costly. And ultimately, we decided on the Zaber ASR one because XY tables usually need to come with a controller that is also expensive, but the Zaber model, the Zaber ASR, came with a microcontroller that automatically detects it, which made our lives much, much easier in regards to programming and controlling the XY table.
In order to be able to operate the spectrometer, the computer utilized must be capable of installing and running MATLAB, as well as all the supporting libraries that allow communication between the software and the various hardware components that make up our system. The team explored 3 different computer options that were readily available, and after some deliberation, we decided to go with the highlighted ZenBook. The reason we chose this computer is because it had the largest storage capacity to hold all the pictures and data collected by the spectrometer, the most amount of RAM available to complete these calculations, and the speed increase of the SSD HDD hybrid was an added bonus. The image on the left is a prototype of the GUI that will be used to control the spectrometer and allow communication between the user and the system itself. In order to add a degree of portability to the system, we made it so the user has to manually choose the communication port that the motor and laser is plugged into before initializing the component and connecting to it. Doing so allows the user to connect their computer, run the spectrometer, obtain their spectrum, unplug their computer, and return to their workspace. Other features include turning the laser on or off and positioning the motor so that a specific sample in the well plate is analyzed. So this is the software block diagram. It demonstrates how the software works with the various hardware components in our system. The first thing you're gonna do is run the MATLAB program. Once this is done, you'll see the GUI that I showed a few slides ago. And what you're going to do is you are going to then select the ports that the hardware components are connected to. You can determine which ports those are by going into Device Manager. Once those are correctly selected, you're able to initialize. Once those are initialized, they'll be connected, and you will see message appear in the message box on the top left that say whether each component is ready. Once the motor and laser are ready, you'll be able to initialize the spectrometer, and at that point, all three components are ready, and you can begin to run the spectrometer itself. The first thing you're going to want to do when running spectrometer is positioning the well plate over the laser. Um, you're going to want to position the well plate so that the sample itself is over the laser, because that's what the laser will be going through. Um, Once you've turned on the laser, the spectrometer will run, the camera will start taking pictures, and after a while, the spectrum itself will be collected. You can then turn off the laser. The software will perform the Fourier transformations and other calculations to get the actual graph that means something to people. Once you have this, you can export it, clear the spectrum, position the well plate over the next sample you wish to analyze, and this process starts again. So Fourier transformations are actually vital to being able to generate the waveform that means something, the spectrometer results. So what happens when you run the lasers is that a camera takes pictures of the light that comes out through the sample. This camera is called the IDSI, and it is what actually converts these images into mathematical matrices. You can see an example of one of those images on the top left. They don't look like much, but after a series of conversions and calculations and eventually a Fourier transform, um, the numerical matrices are transformed into a graph. The graph is what you see at the bottom left, and it has peaks at certain wavelengths. And each of these wavelengths corresponds to a specific chemical makeup or chemical signature, and these combined signatures will tell you what exactly is present in the sample being analyzed.
The majority of our budget was spent on the laser and the XY tables, especially since they're precision scientific instruments. We weren't really expecting them to be cheap to begin with, and our sponsor also had a very good idea of how much they would cost. We're still waiting on the invoices on those, so we will update our budget table as soon as we will get those. But other than that, the majority of our expensive were in the lenses and the beam splitters and the detector, which was also expected. And according to our sponsor, we were actually able to stay within budget, which is really great news for us. Our progress so far on our project has consisted mainly of connecting our laser and its controller to our computer and getting it to operate as needed, turning it on, adjusting the power settings, current settings, and such. We managed to program our XY table to move as needed and to hold every single well sample in its proper location with the precision needed. And it's also able to adjust the distance between wells and such to accommodate different well plates. Right now, we are working on the assembly of the laser components and glasses specifically, since we need the beam splitter and detector to be installed before we can begin our spectrometer usage and, scanning samples of water.